get to the
Oh, I
next
did-
one,
I
you
did.
just click like
Yeah.
that. One of those, it's gonna be down or right. Unless you want me to do it, I can even do it, change slide.
No.
Okay.
So yeah, doing magic squares, it's far more interesting of a topic than I originally suppose. All sorts of combinations, connections to ancient times, to Euler, sorry. And yeah, let's go. So this is a quote, to sort of introduce the concept, because I'm going to take a little bit of a philosophical perspective. And I kind of want to rush through this so I can get to the math, because I think that's the best part. So it seems to this guy that its magic squares seem to betray some sort of hidden intelligence behind the ordering of the numbers in the square, and find symbolic value in it. So this is a brief history from east to west. This is started out with the Lo Shu, which we will go over. Lo Shu Square to India. Although it moved to India, it had a consistent development in China, while simultaneously, and made its way to Europe. European Renaissance art, Euler, and then Ben Franklin, who actually had a pretty significant contribution to magic squares. But nobody really knows how he made it, but there's has some unique properties. This is the Lo Shu, its creation myth, China, sort of like almost like Adam and Eve. And there's a big flood, there's people, the king offered sacrifices, and the turtle emerged from the river with a magic square on its back. So it has some sort of mystical, symbolic significance to China, as well as Europe, as we'll see. And this is some European art. This is probably the most famous example. The Albrecht Dürer is Melancholia. This is his own magic square. It's order 4. And there's some apparently, like, so the 1 and the 4 is supposed to be AD for his officials, and it's made in 1514. So he probably used the Euler Greco-Latin method of constructing squares, which uses two orthogonal matrices, basically.
What about this? Where do you remember where that came from? The other
It's in Spain.
Yeah.
I don't know.
Yeah.
This one's not, it's got 2, it's not a real magic square,
Yeah,
but it's a good attempt, so I put it.
yeah.
No, I mean, it was intentional. There's actually like many different categories.
Yeah.
So,
Yeah, super cool.
yeah. We'll go to the philosophy. So numbers have meaning in the sense that Pythagoras thought that the one's God, like literally, because all math can basically be reduced to the sum of numbers, whether it's an integral or summation, and ultimately, well, he worked with natural numbers, and all natural numbers could be thought of as the sum of 1. So 1 created all the numbers, therefore 1 is God. He thought that the universe was made of number. So from that perspective, we'll look at first of all, does anyone have any idea what a magical square could possibly symbolize? Like, why would it be in a Chinese creation myth? What's the mystical significance of it? Well, something to think about. So in the Oriental tradition, or in China, this is originally with the Lo Shu squares. They didn't use numbers, they used just
sort of math to just use like points. And then this was about, it's estimated to be about 4,000 years ago. And this is far more recent. This is like Renaissance times. And this is example of cipher, Hebrew cipher. So 1, 2, 3, 4, 5, 6, 7, 8, 9, order 9 magic square. And we'll show a brief example of order 4 using Hebrew to show how they would communicate with planetary spirits using magic squares. Allegedly. So this is part that's probably most interesting. You know, I'm a big fan of B.B. King. I have been for a very long time. It is basically sort of a logical. It follows from just the idea of anything pretty logically. So these essentially the most important symbols are the 8 trigrams, which is 2 to the 3, because there's each line can be interlinked. So got 8 right there, and then you combine 2 trigrams together and you get 64 hexagrams around the middle. I mean around the boundary. And notice that there's a 5. This is a 5. And this see these outer arrangement of trigrams is the Lo-Shu square. This is it's called the earlier heaven arrangement. The sequences of the hexagrams and trigrams are very important. They're not completely obvious, and I think there's recently been like a combinatorial explanation for why they are the way they are. And originally the sequence was this right here, which is pretty intuitive because you think of the idea of balance. Okay, well you'd have 3 yang balanced with 3 yin. And it's like a binary system. Think of them as inverses of each other. Because that's not how this outer arrangement is structured. This is, well, it looks like this for these, but then you start noticing like, why would 3 yang be the inverse or balance out this symbol? And why would that balance out that? That's because of the structured based on the magic square. So I think there should be an animation that shows the connection. Yeah. It's not a completely intuitive, but I was very satisfied when I found this. It took me forever to find it. And so yes, this is the connection.
And so the horizontal bars with, I call them poles,
Right.
they're representing numbers. Do they?
Yes.
Yeah.
They're basically,
What do you
well,
think?
they represent, I mean, they can.
Yeah,
I mean, they're 8 elements.
yeah,
So they're,
there should be a way to associate them, anyway.
so yeah, so the 3 by order 3 magic square, it's 9. So they put and they have 5, another system that has 5 elements in the middle, and they put the 8 around them. And yes, the original, it's called the earlier heaven sequence, was basically like our binary system. And then the later one called the King Wen later heaven sequence is it's not intuitive until you realize it's based on the Lo-Shu square. And this is an example of feng shui. It's just a random image, it's not. But this is the sort of another way they use it. They use it in also ritual ceremonies to determine not just furniture, but just how people move in the rituals. And it's based on another myth of a very similar square. And where the king, to stop the flood, the king basically walk the path of Magic Square. Now, the Renaissance went wild with the Magic Square. As you can see, there's lots of occult sort of interpretations of it. And this is the Agrippa's that's sort of like the sort of how to say it, like probably the biggest influence of it that started the whole occult movement in the Renaissance, probably Agrippa's 3 books on philosophy. And these are the days of the weeks. So Sunday, Monday, Tuesday, Wednesday, Thursday. Like that's why the days are ordered the way they are. They're correlated with the like Greek and Roman gods. You know, the planets ultimately. And Kabbalah was big in the Renaissance too, with Leibniz and Newton. And let's see, these spheres, Sephiroth, and they're associated, they have numbers. They're also associated with planets, it's not very clear here. And that'll be important for how they sort of communicated with spirits, how they determine which square would allow them to communicate to which planets, planetary spirits. Now, this is an interesting coincidence. Gossel, Mr. Gossel, I don't know if anyone's familiar with him, he works here. And it turns out I was showing him a presentation.
I'm gonna just minimize the people so we can see more.
Okay.
You keep going, I'm listening.
Showed me the slides as I stole them. And any slides that I used, I put his face up there. So this is his, yeah, he was probably around 20 something, well, probably your guys' age. And this is the Dura Magic Square that we saw, the picture in the Renaissance of the Melancholia. As you can see, it's the same square with the date and his initials. Franklin Magic Square.
Every bit rose up to 260. That's interesting. I've never heard of that before.
Yeah, he put his own spin on it, which is apparently he was like a clerk in some courthouse and he wasn't allowed to talk, so he just figured out his own way to make magic squares. I'm not sure that people know his method, but he did leave the squares behind, so they do have interesting properties. This is Euler's. This one, Euler, of course, Euler would make contributions to this field of mathematics. And this one's based on chess pieces. Jeez. No idea what this guy is. So I'm guessing that's Terence Tao. Famous mathematician. This is his, I don't know, so he made his own.
Okay, you're sure you're about to answer my question. I have to read the diagonal going.
Yeah, so he probably, I'm guessing he used the Euler's method, but I could show you the brief overview of it. It's pretty straightforward. It uses like the two orthogonal matrices of what they're called Leibniz squares.
I see. So semi-magic means effectively that rows and columns have a common sum, but the diagonals may not. Is that what? Yeah.
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 It's really, yeah, I'm always learning about new
Yeah.
types of magic squares. It's like perfect. There's all sorts. Applications, not so much. There's cryptography, communication with spiritual entities. we call that an application. There is, I mean, there's a lot of research being done in it. So that's something, and the Mount Petition Hardy. The apologia to.
Yeah.
Something like that. Like, it turned out all of his work turned out to be super useful. So I kind of think that maybe something like that, some magic squares, something that I think it might be useful someday, just not today. So, and now I want to show you some math. So.
And at least the black do work reasonably well, and I'm just gonna in here move this towards the. Oh, I have to stop sharing, sorry, I have to stop share. And it's, yeah, you're moved up so people can see you, I'm just gonna, y'all can actually see the board, but online, they can see right there. Is that what you're gonna do? Yeah. And they can see up to like the purple.
Sure, so that's how it works. Yeah, that's in case you want to follow along. I find this stuff really interesting. It's pretty easy. First, there's one magic square. First of all, we might want to define what a magic square is. It is sort of like n by n matrix of this thing. And if it's normal, which that's just what I'm going to call a magic square, then it's 1, 2, ... squared. So for a order 1. It's pretty straightforward. The 1 there. Number 2 is more interesting. It's the only magic square that actually cannot be constructed. So I'll do the short proof. There's a couple ways to prove this. You could do this on even, or that's how I originally tried to do it myself on numbers. So no, actually, I should probably introduce what a magical constant is. So all the numbers have to add up to a magic constant. So actually, we could just get that for now. So all of them have to add up to the same number. So we know A plus B, A plus C. And this is a contradiction because you subtract A from both sides, the B, C, and they're not the same. And another way to do it is by the magical constant. And so I'll derive it really quick. It's pretty interesting. So, it's a distinct, this matrix of distinct numbers from 1 to n. We know that the sum of the natural numbers from 1 to n is the Gaussian. Sum of this equals n plus 1. I think we even went over this. So we know that, and if we change it to like n squared, this is this one. So we know you add all the numbers in a magic square together, you get this number. But we want the number of each row, column, main diagonal. So we divide that by n, and we get Cn. And 1, over 2. And that will give us our magic constant. This is an order 2. That means that C2 equals 2. 1, 2. 5 odd number. This is how I originally tried to prove it. So we know A plus B equals 5. So in order for this to be true, say maybe A is odd, then B must be even. This, but if A is odd, then C must be even. But that means this diagonal, 2 even numbers cannot possibly be here. So bad square. So things get pretty interesting with it. This is sort of a general technique for pre. But it works for all odd, and it's like shows it's a pattern that reoccurs in most constructions where you generally sort of conventionally just start there at the top of it and go up and right, but since you wrap around and you get there, you go up and right, go up and right. Problems, the space is taken, so you go down. So let's see, go up and right. Uh-oh. 7. Right. And this is, I don't think this is Low-Shoe square, but I mean, if you rotate it, it would be, I think there's only one, there's only one, like all magic 3 squares are isomorphic. You could rotate them and get the same one. So it's essentially the Low-Shoe square, maybe you could fill your head or something.
If it's true, that would mean 5 is always in the middle, it's always in the middle, there's no way to not have it in the middle, is that obvious and there's being stupid?
No, that's a good point. And so that's actually what this term right here is. And so yeah, so the middle square of the odd square is actually is always of a normal magic square is only n squared plus 1 or and then even square is over
Yeah.
the middle.
Yeah,
Um,
sorry, you're right, go on. You keep going, we only have 5 minutes, I want to see what the next one is.
yeah. So four, this is another pattern. There's really, I could go on for a very long time. So this is a different strategy, but it's like there's basically the other ones are they borrow techniques from these, so like these type of strategies. So this one index them basically. And then you take the diagonals and you reverse them. Or you could go, you're familiar with algebraic linear optimization. Something like n squared plus 1 minus. And you apply this to the diagonals and you get something. This. So I guess we can check the magic constant should be 4 12 minus 17. Or. 23. This one,
Which right, the top row is what was Brewer's bottom row, so at least it's in the ballpark,
really?
yeah. One, 4, 14, 15.
Yeah, it looks like it might be right. I may have made a small mistake, but that's the idea.
Yeah.
And then I'll briefly go over, oh shoot.
Oh, yeah,
I have,
yes.
Overstepped my approval boundary. It's interesting, so then you could apply this strategy for all odds, but the rules get a little more complicated, you could split them into 4 and plus 2. And like, just 4 and. 4 and. We can do. Say, for example, 8 would be 4 n. And essentially what we do is. Same thing. It's like a recursive process, like a recursive algorithm. So instead of doing it diagonals, you do it four crosses kind of. And the most interesting, which I'll wrap things up, this is the most interesting method. It's called the I need to make some room. It's on the backside of the worksheet. It's called the Lux, Longley's Lux method. And basically, you could use it on a order 6 magic square, but it doesn't use its full properties of the sort of algorithm. So it's better using the order 10. Right. So basically, what you do is you create sort of like a map. 5 by 5. Basically split these into like a 5 by 5 of like 2 by 2. And then you fill these up. This is like the esoteric part where you're probably thinking like, what the heck's going on? You fill up the first. So this is 2 n plus 2. So what is that? 4. Wait, is that right?
Yeah, it is 4, you're right.
Or so you fill the first n minus 1, which is 3 rows with L's. And this is and you fill the next one with U's. No, this is n. Shoot, I don't know. But this is how it looks. And then you switch these, and this is the mathematician Conway, who recently died, COVID actually. And it spells flux or wool thing. And look at it. And I think the L, this will tell you how to fill in squares. So L 1, 2, 3, 4. I have it in there. So this looks like an L. It's like
Yeah.
Get an X. Start just like the order 3, start at the top name. And then see it's an L. So we start number. 1, 2, 3, 4, go up. Right. What is this, X? So you go 5, 6.
Oh, okay, now I understand, right,
Yeah.
yes, okay. I
and
understand,
there,
it's fascinating.
2, 7, 8, 9, 10. I think it's-
Yeah,
And yeah, you keep going the process.
yeah,
Should result in a magic square, all things according to plan.
oh, that's fascinating, so we